So in this next series of lectures, we're going to see the important topic of scheduling. In particular, today we're going to see single processor scheduling. But let's start from a higher level. So why do you need scheduling at all? Well, in any cloud computing system, you have multiple tasks to schedule. For instance, if you just consider your laptop or workstation or even your mobile device, there are multiple processes that are running on that device. On your laptop, you have your browser running, your editor running, maybe you have an IDE running, and essentially the operating system needs to schedule these processes across the limited resources that it has. Primarily, the main resource is the processor or the CPU, and if you have a single core OS or single core machine, then you have a particular series of scheduling problems. And of course, you might have a multi-core machine where you might be able to schedule multiple processes simultaneously. But once again, typically the number of processes is much more than the number of processors that you have, the number of CPU that you have. And so scheduling here becomes a challenge. In a cloud computing cluster, you might have a Hadoop job running, and that Hadoop job has multiple tasks. So the cluster needs to decide where to schedule each task of the Hadoop job. You might have multiple Hadoop jobs, each with their own tasks, and they might be competing for resources. And now the cloud scheduler needs to decide where to schedule these different tasks of these different Hadoop jobs. You have a large number of tasks, and there are limited resources that these tasks absolutely need. So each task typically needs some amount of processing capacity, a processor, some amount of memory, and of course it needs disk and network as well. But typically scheduling algorithms vary about processor and memory because these are the resources for which there is most contention. There are two goals of scheduling algorithms. The first is to increase the throughput, or the number of jobs you can execute per time unit. And related to that is reducing the response time, or reducing the time that it takes one job to complete in your system. Okay, so essentially we'll just take into account the completion time of jobs. The second is high utilization of resources. You want your resource to be utilized as much as possible. You want all of your processors to be utilized 100% of the time, all of your memory to be utilized 100% of the time, so that you're making the most out of the resources that you invested your money in. So let's look at single processor scheduling in this lecture. So you have just one processor in this particular problem, and you might have multiple tasks that are trying to compete for these resources. In this example, I have three tasks: task 1, task 2, task 3. Task 1 arrives at time 0. It has a running time of 10 time units. Task 2 arrives at time 6. It has a running time of 5 time units. And task 3 arrives at time 8. It has a running time of 3 time units. So you need to decide when to schedule each of these tasks at what time on this single processor. So one of the basic scheduling algorithms is what is known as FIFO, or first in, first out. This is also known as FCFS, or first come, first serve. So in this algorithm, you maintain the tasks in a queue in the order in which the tasks arrived. So tasks that arrived earlier are ahead in the queue, tasks that arrived later are later on in the queue. Whenever a processor is free, you dequeue the task at the head of the queue and you schedule it on the processor. So for instance, at time 0, when task 1 arrives, place it in the queue. It's the only task right now, and so it executes until time 6. At that point, task 2 arrives, it's placed in the queue, but then task 1 is still executing on the processor, so task 1 is allowed to complete. At time 8, task 3 arrives and it's added to the queue, but after task 2. At time 10, when task 1 finishes, the head of the queue is task 2, so that's dequeued and it's scheduled on the processor. It runs until completion, which happens at time 15, at which time, once again, the head of the queue, which is task 3 now, is dequeued and is scheduled on the processor. Task 3 finishes at time 18. So task 1 finished at time 10, task 2, which arrived second, finished at time 15, task 3, which arrived last, finished at time 18. This is the FIFO algorithm, and even though we are discussing it for a single processor scenario here, FIFO is in fact used by a variety of different cloud computing schedulers, including the Hadoop scheduler. So how about the performance of FIFO or FCFS? Well, the average completion time, which is really what we care about, we want completion time to be as small as possible, may be kind of high for FIFO. For instance, for example, the average completion time can be calculated by adding the completion times for the three tasks and then dividing them by 3. So that's 10 plus 15 plus 18 by 3, or 43 by 3, or 14.33 time units. This is on the higher side, I'm telling you, but can we do better than 14.33? What is another scheduling algorithm that does better than 14.33? Well, that better scheduling algorithm is known as shortest task first. So in this particular approach, again, you maintain all the tasks in a queue, but not in the order of arrival. Instead, you maintain the tasks in increasing order of running time. So tasks that are shorter are maintained towards the head of the queue, and tasks that are longer are maintained at the tail of the queue. Whenever the processor is free, you dequeue the head task and you schedule it on the processor. So once again, let's go to an example where we have three tasks, tasks 1, 2, and 3 with task lengths of 10, 5, and 3. The arrival times here are all zeros because I want to show you an example where the STF scheduling algorithm in fact has to make decisions among tasks. And so here task 3, which has the shortest length, is chosen to run first. It starts running at time 0, finishes at time 3, at which point task 2, which is the next shortest task, is scheduled. It runs from time 3, finishes at time 8, and finally task 1, the longest task, is run from time 8 to time 18. So this is the shortest task first scheduling algorithm, STF. Sometimes this algorithm is also known as SJF, or shortest job first scheduling algorithm. But we'll stick with STF because I want to maintain the uniformity of terminology here. So why does STF do better than FIFO? Well, STF in fact can be proved, formally proved, to create the shortest or the smallest average completion time among all possible scheduling approaches for a single processor system. So given a single processor system and a bunch of tasks that you need to schedule, among all the possible scheduling strategies that you might have, the STF strategy gives you the smallest average completion time. For instance, for our previous example, the average completion time of STF is the sum of the three completion times for the three tasks divided by 3, which happens to be 18 plus 8 plus 3 divided by 3, which is 29 by 3, which is 9.66. And this is much smaller than the completion time of 14.33, which we had for the FIFO or FCFS approach. The other nice thing about STF is that it is actually a special case of what is known as priority scheduling. In this particular STF scheduling approach, we sorted the tasks according to their running time, and in fact we treated the running time as a priority, but instead the priority might be specified by the user. For instance, the user might specify a higher priority for interactive tasks that involve keyboard and mouse input, but a lower priority for background batch tasks that don't require any user input but have an output at the end of a long run. You would always place the higher priority tasks at the head of the queue, and whenever those tasks wanted to compute, you let them run on the processor. A third scheduling algorithm is what is known as round-robin scheduling algorithm. In this scheduling algorithm, you allow tasks to be run in pieces or in chunks. In other words, you split up a task into small quanta, and the quanta may be just a small time unit, such as say 1 time unit as in our example here, and you run only a portion of a task at the head of the queue. When that portion of the task is done, you preempt that task. In other words, you save the task of the state of that task, and then you add that task back again to the tail of the queue. You take the head of the queue task again, whatever task happens to be the head of the queue, and then you start running that task at the processor. In order to run this again, you may need to bring back in the saved state of that task if it was preempted in the past. So again, in our example, we go back to our example of three tasks 1, 2, and 3, which arrive at times 0, 6, and 8 respectively. So task 1 arrives first. It's the only one, so it's run so that it occupies the entire processor until time 6, at which point of time task 2 arrives, and so task 2 is now run for 1 time unit. And then when it's run for 1 time unit, it is put back at the end of the queue, and task 1 is allowed to run. So at this point of time, task 1 has run for 6 plus 1, 7 time units. Task 2 has run for only 1 time unit. Then at time 8, task 3 arrives, and now it is allowed to run for 1 time unit because it's at the head of the queue. And now after it runs for 1 time unit, it's put at the tail of the queue, and then task 1 and task 2 are allowed to run, and then again task 3. Okay, so this pattern repeats again. Then again you have all the 3 tasks run, and at this point of time task 1 has run for 9 time units. You have 6 plus 3 greens, that's 9 greens. Task 2 has run for 3 time units, and task 3 has, the blue ones, has run for 3 time units, 1, 2, and 3. And so task 3 is actually done at time 15. Okay. So after this, you have only task 1 and task 2 to cycle through, so you round robin through them, and then this continues for a while. At this point of time, actually task 1 is done at time instant 17. Round robin essentially gives a fair share of the resource, the processor, to all the tasks that are present in the system. So when do you prefer round robin, and when do you prefer shortest task first or FIFO? Well, round robin is more preferable for interactive applications that periodically need access to the processor so that they can run and process things like the keyboard input, the mouse input, and so on and so forth. Okay, these are applications where the user needs quick responses from the system. On the other hand, FIFO or shortest task first is more preferable for batch applications where the user submits a job, goes away for a while, and then comes back later on to get the result. For these, you don't necessarily need to have applications that run in Quanta, but you can give them access to the CPU all at once. And in fact, there are many hybrid scheduling approaches that combine both the round robin that we have seen and the FIFO STF that we have seen. These are known as hierarchical approaches. So to wrap up our discussion of single processor scheduling algorithms, we've discussed some of the classical algorithms, including FIFO or FCFS, which schedules tasks in the order of arrival, shortest task first, which schedules the smaller tasks first, and priority, which is a generalized case of the shortest task first scheduling, where each task is scheduled in the order of the user specified priority. Also, round robin scheduling algorithms, which are well matched for interactive applications, where each task is given small shares to run. And of course, this is only a sliver of the many scheduling algorithms that are out there, which I encourage you to look up. We haven't discussed cloud scheduling yet, and that's what we're going to discuss in the next lecture in this series.